Loran Novacek with AeriNOx, and first I'd just like to say, much like Tyler did earlier, was just to thank everybody for attending, coming out on maybe this is a normal day for you guys. From where I'm at in Colorado, it's usually a little bit sunnier. We still get the days, but it's generally a little bit nicer most of the time. I want to thank TNT for really kind of bringing us up here and inviting us to speak at the conference, and then a couple of my colleagues that came along with me that made certainly a much longer journey to make it here than I did, but I certainly want to thank everybody here. I'm with AeriNOx, which does exhaust emissions controls for stationary equipment. I don't deal with anything on mobile equipment. I don't deal with anything in the automotive industry. Typically, you find that industry's very competitive. Pennies tend to make more sense than dollars and thousands in that industry, so we tend to shy away from that. But from a technology perspective, you'll find that that's really what's leading the pack, right? So for many of you, you're probably already familiar with SCR. Might be just phrased a little bit differently, right? So if you think of some of the General Motors, the Fords, the Dodge pickup trucks, the diesel trucks around the market right now, they have a DEF system, which is nothing more than an SCR system on the vehicle already. So when you pull up to your truck station to fill up for diesel, you may have a DEF tank or a DEF system that you have to fill up with it. This is very similar to it. So some of you are probably already, much like you find out in the States, is they've already removed some of the systems, right? People are generally not a fan of exhaust emissions controls. They generally refer to it as a power limiting device on their diesel truck. They want to blow more smoke, they want to make more power, and so a lot of times you'll find in areas within the states, guys like to pull them off. Texas, Louisiana, some places even in Colorado pull them off. But generally speaking, obviously that's not the intention of what the EPA has done. The EPA guides and drives a lot of that technology. The whole idea behind it is to really reduce overall exhaust emissions in the market space. And so this market space that we're talking about now is really an adoption of what automotive has been doing for many years. It's just in the industrial market space, it's intended to last years, not a few thousand hours that you'd find in the automotive market, where you equate it to maybe miles rather than 10s and 20s and 30 years market space. So what I want to do really today is just kind of make you aware of what the technology is, why is it there, and it'll be a good foot placement for really kind of talking and extending this technology into the greenhouse market space. And I'll explain that a little bit later. Well, who is AeriNOx? AeriNOx, two of my colleagues are here with me. It's a joint venture between H&H out of Germany and DCL out of Toronto. The joint venture was put together to support the North American market space. H&H has already had a strong presence in Europe. It's already had a very strong presence in many of the other countries that require exhaust emissions controls. And DCL, that was a piece they were missing for years, was not having SCR technology to take to the North American market. So it was a great opportunity for the two strong leaders in the market space to come together and really support North American market for SCR technologies. Some of the pictures you see at the bottom, really just an indication of the different markets that we're in. We're in power generation, you could call that also CHP in certain applications. We're in many industrial applications, kilns, boilers, and of course the far right picture is marine applications as well. Marine's been adopting it for many, many years, and it just like the industrial market and power gen and CHP has adopted it. The technology is not new. It's from an industry I came from in the oil and gas. It was a market space that it was very common for them to say, well, it's not proven. And it's a very difficult statement to make now and stand behind for those folks, because it's been around the industry for 20 to 30 years, and it's run across various operating conditions. It's been on turbines like the first picture showed. It's been on power generation units that have to run 96, 97% uptime all the time. So the technology is well proven. It's nothing that we're bringing that's new. Slide here just shows really the various locations that we're in. Again, I'm out of Colorado, so I really support all of North America. My colleagues support one out of Germany and one out of the Netherlands. Then our partner DCL is based primarily in Toronto. They've also got a manufacturing shop in Houston. So what is SCR? It's a lot of words, it's a few pictures. Has anybody used or have SCR technology on stationary equipment? Rob has. What, nobody else? Does anybody operate power gen equipment, CHP units? Okay. Rob, you don't count no more. All right, SCR is Selective Catalytic Reduction. It's a little bit different than what you do on a rich burn burner. Rich burns, you just throw on a catalyst and you have a way to manage the air-fuel ratio on the unit. In other words, you're managing how much fuel is going in the engine with a given amount of air. On an SCR system, it requires a reagent. What's a reagent? It means I need ammonia gas. That's what the system requires. How do we get ammonia gas? Comes in a couple different flavors. The most prevalent, the most common in this industry, certainly in power gen and CHP, when we're driving smaller recips, 1, 2, 3 megawatt type applications, it's urea. It's a fertilizer. Right? We spill it on the ground, means nothing. It dries, forms a white powder, wash it off with a hose. It's considered a non-hazardous material by the EPA. I can go to anhydrous, pure ammonia gas, or I can go to an aqueous-based ammonia solution as well. Each type is dependent, what drives the type is dependent on what the application is. If it's a 1, 2, 3 megawatt unit at a greenhouse or a power gen or a CHP facility, stay with urea. Don't even touch ammonia. It's not that it's not better, it's not that it wouldn't be cheaper, it's just going with the ammonia route tends to make the permitting requirements, the transportation and the handling of that reagent much more difficult than it does urea. So urea is definitely the way to go in probably the majority of the applications we're talking here. What changes it when you go to ammonia gas? What are the stipulations? Well, when you get into big turbine applications, when you get into big turbine power plants that are 100, 200, 300 megawatt applications, everybody goes ammonia gas because it's the cheapest. It's the easiest to use. I don't have to use any special equipment to break it down to that ammonia gas. It's already a gas. I just have to mix it. Probably some of the new developments that's been coming out over the last, say, 5, 8 years is really the different catalyst beds that are being used. The traditional catalyst that's been used over the years is a ceramic-based element. So it's extruded. We extrude that element to a certain length that we need. That's what helps define the amount of reductions that we want. But some of the newer technologies that are coming out is based on a metallic. It's a metal foil. Much similar to what you'd find in an automotive type application. Typical working life, it varies. Every application is a little bit different. We always size it for the project. We try to stay away from a standard podium or a standard size. We try to fit the application. We try to fit the SCR system for that particular application itself. But nominally, we would say 16,000 hours. What does that mean? Well, there's almost 8,800 hours in a year, 8,760, right? So that means there's about 2 years of life of catalyst that'll last. Just a quick general layout. I don't want to probably dwell on it too long, because I've got a few pictures that kind of come behind this that'll kind of highlight some of the key components. Each of these, again, are customized in the application, so the top line is really referring to the exhaust components themselves. It's the piece that you see, right? It's the piece that's on your truck that you see the most predominantly. I see the catalyst beds, I see the piping, I see the silencers. Those are the big components. The piece that typically is not seen is the controls. Those can come in a variety of configurations. Again, what drives that configuration is the emissions requirements. What's needed in Ontario, it's not that low. You can get away with generally some pretty small control panels, control systems to get to the levels that you need. When we start taking these into Massachusetts, or you start putting them on turbine applications, and certainly greenhouse applications. Then we modify the controls a little bit because that control system is more important. It's not that this piping's not. It's just that's what gets you to a certain level. What keeps it there are these components right here. It's the brains. There's some of the key components. We need the ability to mix the urea, the ammonia with the exhaust. Doesn't matter what the reagent is. I have to have the means to be able to mix it with the system. Once I get a good mixture, then I go to a catalyst bed. The catalyst bed is what creates that chemical reaction for us to break that NOx down to nothing more than nitrogen and water. That's essentially what we're trying to get to, right? I want to take that NOx, that EPA defined, that Environmental Protection Agency defined exhaust constituent that's not good. It's an ozone precursor. It's a critical component in the environment. I want to break it down. So this is the piece, go back. This is the piece here that's breaking it down, is right at the catalyst bed. Just a different configuration of what we've done in the past. Again, top left is the picture of a metallic-based element. So the difference in metallic versus ceramic is primarily the length of the housing that I need. So those catalyst lengths in a metallic configuration are much, much shorter than they are for a ceramic bed. Dosing. Each of the different reagents have a different type of dosing mechanism that we use. The idea is the same. I still have to get a certain amount of reagent into the exhaust stream, but how I do it is regulated a little bit differently. Some of them I run a little bit of air, some of them I don't use air, but on every one of the systems, I manage it and I monitor it with how much am I putting in. So I'm using a flow meter. So I know exactly how much is being used at any point in time of operation, and then we track it. We got to have a pump system, right? I've got to have a means to get it to the dosing. I got a means to control it from that point and get it to the injector. So I run common-based pressure systems to get it there. So just a couple final pictures to sort of close it out before we transition on. I wanted to really kind of show some pictures of some recent applications. As my colleague will come up here in a little bit, we'll kind of get into more of the CO2. But in many of the greenhouse applications, in many of the, doesn't matter, hospital applications, small manufacturing entities, they may want to run combined heat and power. So in that application, we have exhaust coming in, we have a means to inject our ammonia solution, we have our catalyst bed, that's what's creating the chemical reaction to get the NOx down. After that, I put in a heat exchanger. So that heat exchanger then is a means for us to capture that exhaust heat that's in the exhaust. And then I run it back through a silencer. An important piece here is that most people tend to ignore or maybe tend to forget about is each one of these components that's in the system have a way to reduce exhaust noise. So the common methodology in the past is, well, I have exhaust noise, well, I'm going to buy a silencer. Okay, that's fair. But remember, this catalyst bed has certain noise constraints that it can apply. Sometimes the design of the heat exchanger can also have the ability to control certain emission exhaust noise constituents, depending on the frequency that we're trying to obtain. So it's important when you're looking at the overall system that you take into account all the different factors of it. So don't just size the silencer with overkill. Know that some of the other components can control it as well. What does that mean? It means that I can reduce the cost of maybe the silencer because some of the other components are reducing it. The previous picture was a representation or a 3D model. This is now a picture sort of from the top view looking down. That equipment sitting on the top up here is from a farm out in California where we have to control down to about 6 or 7 ppm of NOx. It's a very low constraint that we have on the emission source out there. And this is just a much closer picture showing the top down of our exhaust heat exchanger, silencer, and then the inlet to our SCR. So in a greenhouse application, what does that mean? It means I'm taking a similar skid to what we're doing on the previous couple slides, and I might add another heat exchanger in the equation to reduce my overall temperature to maybe 50 C before it would go into a greenhouse. And then I do some additional conditioning on it. So I won't get into that too much. So any of the questions that come up for that, we might hold those questions out in the greenhouse for my other colleague to share a little bit more on that. So greenhouse application in the Netherlands. Again, showing the picture, the control system itself. That panel is about 7 feet tall and about 4 feet wide, maybe 2 feet deep. It's a pretty good sized panel. Most of that's comprised of conditioning. We have to be able to monitor the constituents coming out of the engine and make sure it's suitable enough for that greenhouse application. Just a quick reference list. Obviously, we've done quite a few different units over the years in many different locations. With that really kind of covered most of the SCR systems. Is there any general questions we can answer at this time?
Well, I actually I do have a quick question for you, Loran.
Yeah.
I love your accent very much. I just wonder if you'd talk, there's a lot of cannabis guys here in the room. Just wonder if you'd quickly tell us about sort of the lay of the land, the way the industry looks in your state, in the state of Colorado, and the country as a whole.
Sure. Yeah. So as you know, I come from Colorado, which has legalized marijuana several years ago. It's definitely changing the market space for everybody. You see a lot more growth in the medical side, you see a lot more growth in the recreational side. And in greenhouse applications, I think what's been the most unique for at least the US-based states is many of the states that have actually legalized the growth of it and the selling of it is challenged with actually the power and the interconnect side of it. That's probably the biggest piece that we see is many of these facilities that are putting it in have determined that power is their biggest culprit, their biggest user. So power for them might be 3 megawatts, 4, 5, 6, 10. We've got customers that are looking at 20 plus megawatts. And what's difficult is the utility is very difficult to work with in many of those locations to do the interconnect. And what does that mean? It means a growth facility can't happen. It means they can't start up. It means they can put it together, but they can't turn anything on because there is no utility connect. So what a lot of these customers are finding they're doing is they're going to go off grid. They've kind of told the utility, thanks, but no thanks. If you can't get it to me or you can't commit to a date within 6 months, I don't want you. I'll run my own power plant. And from that power plant, then I'll capture my own heat. I'll use that heat for my facility through HVAC or whatever, and then I'm gonna look at CO2 injection as well, because I already use CO2. I'm just gonna use it for as sort of free, right? I'm running the engine for power, I'm running the engine for heat, well, I'm gonna capture the CO2 that's already in that exhaust system. I'm gonna use it as part of my growth process. So that's probably the biggest challenge for us down in the state side is that utility interconnection.